Grazie, thank you everybody. Hi Aude, I can see you. I don't know if you can see me.
Buongiorno.
Hi. So
Can you hear me?
Yes, we can hear you. It's good to see you. It's been quite a while. Hope everything is well. And thank you so much. We are so grateful and honored and happy to have you here with us, even just online. It is truly a great pleasure to introduce today Aude Billard here. Aude is a full professor at EPFL in Lausanne, and she is one of the pioneers of robot learning. She's an IEEE Fellow, ERC Laureate, a member of the Swiss Academy of Science and Engineering. But more than that, she's a true, I'm speaking as a female researcher in a field, she's a true role model. She's the actual definition of the role model. I will never forget my conversations with her when I happened to work and live in Switzerland, several lunches, very good advices, which I never forgot. Thank you. Thank you so much. So today we have a talk. You will talk about your research here. The stage is yours, and please.
Thank you very much, Barbara. Thank you so much for the very kind words. It's been a pleasure, of course, to have all those chats with you, and I look forward to have more. I so much regret to not being able to be with you. I had many commitments, so the invitation came unfortunately too late on a busy agenda. Let me share my screen. No, I cannot. Host disabled participant screen sharing. It's going to be a little bit of a problem. I can try to give a talk in robotics without video, but it's less fun. So if I'm allowed to share screen, that will be awesome. I have to kindly ask the host to give me permission to share screen. In the meantime, let me give a little bit of an introduction to what I want to present. So I would like to give you a little bit of an overview of some part of the work that we do in the lab. It's not going to be comprehensive of all what we do, but it's some part that I really like. It has to do with designing control systems that allow the robots to act super fast. And we're talking about millisecond reaction. So we're looking at ways in which robots can react on the fly if there is a disturbance. And typically something that comes in the way of the robot. It could be an obstacle, a human passing by, or it could be that just the object that you want to pick up or catch is moving very fast and it's not moving as you expect. And you have to compensate for these disturbances. So to do that, you have a few milliseconds, and there is no time to plan, to use Global Planner. So what we have been working on was to design ways in which we can replan in milliseconds. Let me see if I can share my screen now. I cannot share my screen still. How do we do? Barbara, are you still around?
Yes, Aude, we're working on that. We are working on that. Please, is it possible for Professor Billard to share her screen, please? Can you allow her to screen? You should be able to do that. Please try again.
I'm trying, and it still says host disabled participant screen sharing. It's in the setting. If you want, I can log off and log back. Or I can continue telling to the audience all sorts of things about robots. Or I can take questions. Either way, it's fine.
So while we wait for the screen sharing to work, and hopefully it will, I start making questions. I take your suggestion. So what do you see as the biggest challenges right now for robot learning, for lifelong learning, considering they're entering so many robots where the humanoid embodiment is not the main embodiment anymore. So how this combined with the advent of very new sensors that are a little bit changing how we think in our head as researchers, how we perceive the world. What is the signal that comes? What do you see coming next?
So it's many questions in one. The main challenge for lifelong learning is, of course, to be able to learn all the time. And we have extremely few examples, and we still have very few techniques, actually, to be able to learn from incremental data as they come. We do have techniques for this, but we don't have much guarantees. So this is the major hurdle, is to have some guarantees as to how much you learn and how much you lose. Now I hear myself in echo, which
yeah. So they tell me that you
are.
I can
share the screen. So
now you can share the screen. Great, thanks.
Yes, it should work, and then I can come back to your question. Should be able to see my screen now?
Yes,
It seems you can. Yes.
Great,
wonderful.
Thanks.
All right, thank you. Okay, so let me get started so that we move on. We don't have so much time. So as I said in introduction, what I really wanted to talk about is the type of work that we do on learning controller that can act fast. And I always like to start with this example that maybe some of you know, where we have a robot that can catch objects in flight very, very rapidly. And so it's not so much the speed at which the robot moves, because if you pay careful attention, you'll see that the robot doesn't move that fast. It's the object that moves super fast. But what the robot has to do real quick is to adapt to the motion of the object. And what is particularly difficult when you want to catch an object like this one is that you have to orient correctly to be aligned with the particular direction in which you want to catch the object. So here, you want to catch the bottle, so you have to align with the main axis of the bottle. And it becomes even more challenging when you want to catch this type of object, which are half-filled with liquid, because in this case, the issue is that you have a momentum inertia which is not constant. As the bottle flies, the liquid is going to move slightly, and so it's going to imbalance the object, and so the dynamics is very difficult to predict. And it was already difficult before, but it's even more difficult here, and it will very much depend on how you throw the object in the first place. So in order to manage to catch objects like this, you basically really need to have control systems that are very adaptive, fundamentally adaptive, and they can adapt in milliseconds. So in order to explain how we get to that, I will start with the simplest example of all, which is just to put your hand on a ball. So imagine you have a robot that starts from a position A, and you want to put the robot's hand onto that object. So you're going to move the hand and eventually close on the object. And you have to compute a pass. And you say, well, there are paths, I can compute paths, but there are multiple of them. There are actually an infinite number of those paths. So which one should I choose has been a problem out there in robotics for decades, and we have many solutions. It totally depends on the objective function you choose. You start from another initial condition, you have to solve again for this path, and again, you can use multiple ways of doing this, but each time you need to have an objective function and solve for that. So as opposed to solve with an objective function, send that to a solver and then wait until you get a solution, which may be quick or not. It depends on the solver and the number of constraints. The ideal, what you like to have is a closed form solution. By closed form, that means you have an analytical solution. Once you have an analytical solution, you don't have to plan anymore. And if this analytical solution has some particular properties as the one that are drawn here, such that it generates a flow of motion. They are illustrated here. Each of the gray line represents a trajectory in state space. If you have a closed form representation of all those trajectories, then you just have to query your function to know how to move with it, and you can query it at each time step. And the best way to represent this is with what are called dynamical systems. And these are differential equations. Here I show a first order differential one. We often work with first order or second order. Here is velocity control, but you can also do it in acceleration. It's the exact same principle. So imagine that you have such a function. Here is going to be f of x. this generates a set of velocity flow. And if your velocity flow are such that they are stable at where you want to go, then you are ensured that all the paths will eventually lead you to that object. Now, you'll tell, okay, all of this is a static motion, so it's very easy, but what happens if the target moves, as I showed before? And there is a little trick that you can do with such a mathematical representation, is to say, look, I'm going to place the origin of my system onto the ball. And if I do that, then that means that as soon as the object moves, then my entire field moves with it. But if the field moves with it, that's fine, because that means that at every single position in state space, you still have one single trajectory feasible that brings you to the object. And this is in closed form, so you just have to compute f of x at each time step, and it's not even time dependent. And so that gives you an enormous advantage because you don't have to plan, and you are guaranteed to have a feasible solution. Now the big question is, what is f? How can I infer f? There are many ways in which we can do that. At the beginning, we used human demonstration, so we had a human showing to the robot how to do tasks, how to pick up objects. These will give you trajectories, examples of feasible trajectory. More recently, what we've done was to rather generate this trajectory with optimal control, solving for more complex constraints offline, and generate feasible path in space. Once we have that, then we can learn a function, and we can learn this in closed form. So those of you who are familiar with machine learning, you know that there are many techniques that can learn that. It's actually a regression problem. So you want to predict the velocity, which in the particular drawing here will be two-dimensional, but if you're controlling for the hand of a robot, it will be at least three-dimensional, or maybe six, and if you're controlling for all the joints, it may be higher dimensional. But each of those dimensions, each of the velocity, can be estimated through regression. So you could use one technique, which is called SVR, support-vector regression. And if you do that, you get what you see in pink. It's a very accurate representation of the dynamics. However, observe that close to the target, you're actually drifting. And the reason for this is that SVR has a mean square loss when it's optimizing. And so it's going to get very close to zero, which is the velocity you should have at the target, but it's going to be approximately zero, not exactly zero. So it does not guarantee that you will really stop. And a little bit of a velocity, which is non-zero, will let you drift, as we see here. And it will be the same with absolutely any technique, same for neural networks. So what can you do? Well, what you can do is say, okay, I want to explicitly have a convergence to a fixed point, which we can express as saying, okay, there is a point in space for which I want my function to vanish. And now the question is, how can I change the algorithm to learn with support vector machine or with neural networks so that I will stabilize at that point? That means you want to embed stability constraints inside the optimization of the machine learning technique. So to do that, you have to express constraints. And in control, one way to express stability at a point is to use the Lyapunov stability, especially if your function is nonlinear, where you cannot write it explicitly as a multiplication of matrix and the state of the system. So if you want to use Lyapunov stability, you have to say, well, there exists a function v, which is going to be an energy function if you want, that measure that the energy decreases and eventually vanish at the point where you want it to be. But now our problem is twofold. We neither have f nor v. So how do we solve this problem? And so in practice, we've looked at many different ways in which we can address that. I will not go through all of them. I'll just give a glimpse of two of them. So one very first approach that we took was to say, if we observe one particular approach in machine learning to represent such a problem, which is through a probabilistic model where you learn a full density between the distribution of velocity and the distribution of state, when I'm looking for a model like this, what I end up with is a set of Gauss functions, which we see here overlaid, and so it's a slice on each of those Gauss functions, and we have a mixture of those. If we want to predict the velocity from this mixture, we can do it in closed form. We can take the expectation over the conditional of this full density, conditioning the velocity on the state. And we get a linear combination. So observe, first of all, that it's linear, which is nice. And it's a linear combination of linear system. The AKX, BK, X is the state, AK are a set of matrices, BK are a set of vectors. This is very easy to compute. And the HK function are actually just normalization function between 0 and 1. So this is a closed form solution, and it has open parameters that are linear. Now you can set constraints to force stability, and you can derive them here by choosing the simplest Lyapunov function ever, which is a quadratic cost to the point that you want to reach. And you can infer then constraints on these open parameters, the BK and the AK. And you can enforce that basically the energy decreases. So you can write this, and you go back now to the optimization for this particular model, which is a mixture of Gaussian. It's a constraint optimization problem where you maximize for the likelihood or you minimize the mean square error under now a certain number of constraints, among which the stability constraint. You do that, then you get exactly what you want. You get a flow, observe here, you get a flow as we've seen before. You have a very tight match to the actual demonstration, but you also have a guarantee that you stop. And observe also that there is a nice generalization at the bottom where the system generalizes to converge to that position. Now, this was one approach. We then looked at other approach where we relaxed the fact that we're using such a conservative Lyapunov function. We looked at non-conservative functions, so where we directly learn the Lyapunov function and then derive f from the gradient of v. We also showed that we could train unstable dynamical system, learn, for instance, from neural networks or any other approach, and then stabilize it with this approach. And if we don't have demonstration, we can also do it with reinforcement learning, which we have shown in this particular paper. I will not go into detail. So once you have such a system, here is a little demo of what you can do. If you have a ball and you want to reach it, and you know that you will converge to it, even if you generate disturbances on the way as the ball will go down that slope, you will be able to catch it. So you'll see that we're going to generate disturbances. We're either going to lift the slope as it goes, or we've placed obstacles on the way, and this generates really unexpected disturbances. So this is a flow without disturbance, this is a flow with disturbance, and observe how the robot is closing nicely the hands on those, adapting to the motion of the ball, adapting to the different disturbances on the fly and in a few milliseconds to meet the object on time. I like to emphasize that we meet it on time, but there is no time computation. It's implicit. It's implicit in the fact that you're correlated with the state of the object, which is the origin of the system. So as the state of the object is coming closer to you, the origin is coming closer to you, so you do accelerate naturally to meet the object. And that's how you meet the object on time. Now, how do we get from there to be able to catch object flying? One we need, in addition to what we've described so far, is to be able to predict the dynamics of the object. As I mentioned in introduction, if you have an object, a complex object flying, one problem is that the flying dynamics is very nonlinear. And here is a nice example. If you want to catch, whether it's a bottle or this particular tennis racket, what happens is that the grasping point, the point where you want to catch it, is not moving with a ballistic motion. It's actually moving, it's rotating and it's moving backwards and then come back to you and backwards, etc. And the particular dynamics completely depends on how you initialize the flow of motion. And typically, if you change the translational velocity to start with, then you're going to get a very different dynamics. So we can learn these dynamics from few examples. We showed that we could do that with many different techniques. We contrasted many different machine learning models. The best in this particular example for us was support vector regression. So it learned a model that is described here, which is predicting now the translational and rotational acceleration as a function of the position and velocity of the object. On its own, it's not sufficient to have this model because, of course, there is noise as you go, so you can combine this with an extended Kalman filter, and you treat the model that has been learned by support vector regression here as the model for the extended Kalman filter. Since you have a closed form solution, you can compute a derivative and fit that to the Kalman filter. And so once you have this, you just have to combine the two systems. So at runtime, you keep tracking your object, which we do with camera that we have in the room, on the ceiling. We estimate where the object is. We continuously predict the trajectory of the object. We predict where we want to meet the object. But if suddenly, as we make a new measurement, this measurement departs significantly from the estimated one, we recompute a new point where to meet the object, And then we immediately use this adaptation of our dynamical system to control the hand to meet the object at the new location. Now, I described all of this in pure Cartesian space as if I was doing only translation, but the same is done in orientation. So we do orient the object, we do orient the hand to align with the object direction, and this is done by coupling the two dynamical systems, one for orientation and one for position. I don't have the time to explain this, but this is documented in the associated publication. Now, this gives us very nice demo like this one where you can catch the object in flight and you have fairly good performances. Performances are good. They're really good given the complexity of the task, but the performances are not perfect. It's about 60% performance when we did the systematic test. Now, you may ask, why do we incur failure? And one reason for the failure is the following. Sometimes you just barely catch it. These are a few examples where you really barely make it. And you see especially the difficulty is to catch the object in the hand and to hold it within the finger of the hand. There are a couple of failure. There were quite a lot of failure actually among this 40% that were due to what you're seeing here. If you observe it, what happens is that the racket bounces before you close. So you actually meet the object, but you don't have the time to close your finger on it. And this is not just because you're trying to catch such a complex object as a racket. It actually happens also when you're trying to catch just a ball like this. So the reason for that is a hardware problem. It's just that your hand is not closing fast enough. So we could have stopped at that and look, just buy a better hardware and move on. But we thought it was an opportunity to also design a smarter controller. Because as surprising as this may appear, humans are actually quite good at catching balls, and they're not as quick as robots. So we were interested to understand why humans are so good, and we got some insight into that thanks to a collaboration we had with Andrea Davella, who's a professor in Rome, and he was studying catching in humans. And he observed that when people catch, they actually don't stop when the ball is getting into the hand. They are moving like this. They are moving a little bit in orbit with the object. And this is really smart because it has many advantages. One is that you can slow down the object as you move, but not directly stop it. So you don't have this bouncing effect. Second is that you still have a bit of time to adjust the position of your finger and possibly also the orientation of your wrist. So we thought, okay, can we do the same with our algorithm? And yes, it's fairly easy to do it. So you start with the dynamical system as I presented before. You start with a function that reaches eventually to the object, asymptotically stable at this. But as opposed to stop at the object, you don't guarantee now stability at the object. What you want is actually to move with the object. So what you want now is to track the velocity of the object. So your stability point is no longer in state space, but it's in velocity space. You want your motion of the hand to now stabilize at a certain velocity. And when I say a velocity, it's not the amplitude, just the amplitude, but it's also the orientation of the velocity of the object. So you start with an estimation of how the object is flying in the world, and now you're using this estimate to align the velocity of your hand once you are within the orbit or within the trajectory of the object to move with it, to continue moving. And you can do this by simply switching between two stable dynamical systems. One is stable in state space, that means it moves as fast as possible to meet the object in flight. And the second is aligning the velocity as fast as possible to the velocity of the object. So this was shown in the exhibit at the KUKA Award. It was used by many different people. Success rate is close to 100%. Such a simple strategy, really based on human ways of doing things, buys you a lot more than buying a better hardware. So I'll move on to the next step. We exploit a lot of the notion of coupling across dynamical system, and we thought one way to do so would be now to start coordinating multi-arm system. Why? Because as you see in this video, we often do multi-arm manipulation in real life and also in the industry. So since we are able to control very rapidly for one robotic arm, can we do the same for two robotic arms, and can we further make sure that these robotic arms move in synchrony and adapt in synchrony? That's the most important part. So our task now is to coordinate two robot arms to catch an object moving, as we've done before, but the difficulty increases now because we have two arms and they need to meet this object simultaneously. So we must track the object as we've seen before. We must control for simultaneous motion of the two arms for simultaneous grasping at the same time. And we need to be able to enforce that we have robustness if there are disturbances on the way such that the object is moving. So we have trajectory of the object as before. What we can always assume is that we have an explicit expression for the robot's workspace, which there are many different ways of having this. We usually learn that. I will not explain here how we do that. There are ways in which you can explicitly learn the feasible workspace of the two robots. And further, you can use then this workspace to determine the grasping point, or the point where you will be able to meet the object in such a way that it's feasible for both robots. This is going to be the intercept point. Now, how can you synchronize the two robot arms? Well, you can do that with this notion of virtual object that I illustrate here. Imagine that you have an object which is already linking the two robot arms, and that this object is now stable, asymptotically stable, to the trajectory of the real object. So this object is flying virtually towards the real object. But because the two robot arms are linked to this virtual object, then this virtual object is bringing the two arms to the object that you want to intercept. So this notion of virtual object, if you want, is like a virtual constraint that forces the two arms to move together. And the fact that this virtual object is now anchored onto the real object allows you to enforce that you will have a coordination, simultaneous coordination that asymptotically reaches the desired object. So here is a slowdown video of how this can be used to do what I demonstrated at the beginning, which is to catch an object that is given to a pair of arms by a human. This you've seen Nadia Figueroa, and here is Sina Mirazavi, both of whom developed this system. This was demonstrated also at the KUKA Innovation Awards, so with many different people trying the system in and out, and it's very robust and very stable. All of this is done in slow motion. So of course, in slow motion, everything is easier. Our goal in the lab is to show that our algorithms, because they are computed in closed form, they can compute things very rapidly. So we went and made a demo of this very fast ability to catch things in flight. And here is the demo. There are a couple of these. You can see a few movies of that on our website. Here what we are doing is that we are flying a flexible bar. And we are sending this flexible bar to this pair of robots, and they have to catch it in real time. So why a flexible bar? Because it's interesting, because it's flexible. So same as what we've seen for the object in introduction, they are not full. They don't have a dynamics that you can explicitly write. So it's very complex because it completely depends on how you started off the initial motion of the bar, and you have to then adapt at runtime. Observe that the two robot arms do adapt. They do meet their respective grasping point on the two ends of the bar, but they travel with a completely different path. Sometimes one will go up and the other one will go down, and conversely. Nothing is prescribed for starter because it totally depends on how you're sending the bar. And this is the adaptation that you have, which is completely dependent on this dynamical system. Each of the robots has this virtual grasping point, and it's led to this virtual grasping point through these virtual objects that forces the two robots to move simultaneously. And the anchor on this virtual object, and the fact the virtual object is also tracking the bar, speeds up or slows down the two robot arms and forces them to move at the same speed as the object. Observe also that all of our videos are slowed down, they're not accelerated, and they're slowed down for you to be able to appreciate this motion of the object and the motion of the robot. They're slowed down here 8 times. We absolutely wanted to port that to a humanoid robot, to have the humanoid robot catching objects in flight. So this was the work done by Sung-Soo Kim during his PhD. He was also the main person who started this work early on for catching objects in flight it was a hammer at the time and not a racket, and then he moved to the racket. Now I'll tell you, we were successful or not. Problem is that the humanoid is slow, so we haven't been able to really do that as fast as you've seen before, but I believe that we had the technology for this. We just miss a platform which is fast enough. So what Sensor developed was to use the object trajectory prediction that we had before, to compute the best catching pose prediction that we had before, and then to control for the arm hand control, a little bit the same as what you have for a single arm, but added to that to be able to learn a stability region for the lower body control. Because when you want a robot to catch an object in flight, and it's a human robot, the additional difficulty is to stabilize the center of mass as you do so. So I will not go into the detail. If you're interested, it's in the thesis. But basically what he did was to learn now a feasible dynamics for the center of mass. And he represented that by a dynamical system. He represented the fact that the center of mass needs not to move further away from a certain region. And the center of mass is moving with a dynamics which is coupled to the dynamics of the arm being coupled to the dynamics of the object. And so this triple coupling allows you to catch things on time. Now, these are the simple video that we have where the robots can adapt the motion and still stabilize, remain stable within its polygon of stability, and still meet the object in flight. On the left-hand side, all what you have is a mock-up of that with a robot. We couldn't do that with a real object because an object will fly much faster than the robot does move in reality. If I have a bit more time, I would like to quickly present some work that we have done on extending this for obstacle avoidance. So of course, it's interesting to do this motion in real time if we can also avoid obstacle. There is a very neat way to do so, still using the same dynamical system approach. So think of this function x dot equal f of x, which drives our system to go from one place to the next. We can now add a modulation from the obstacle, which is a simple multiplication m of x times f of x. So what is m of x? M of x is a matrix that will modulate the original flow of f of x in such a way that it will prevent it from penetrating the obstacle. So let me represent how we can do that. Imagine that you have an obstacle like here, and you have an explicit expression for the obstacle boundary. You know the shape of the object, and this expression for the shape of the object is given by a function that you have in closed form, gamma of x. You can learn it with machine learning techniques. There are many ways in which you can learn that. For those of you familiar with GP, Gaussian process, it's one approach that has been used extensively to model the surface of objects. So you have this function. And what you also have often when you learn it with machine learning is that you have not just the function as the function on the boundary of the object, but you have a notion of a distance. And you can force the machine learning algorithm to learn that the function has a specific value on the object, for instance, here 1, and then outside the object is going to be bigger than 1, and inside is going to be lower than 1. So if you have this, what you can do is construct your modulation in such a way to deflect the flow at the boundary explicitly. This is illustrated on the right-hand side. You can construct your m of x by eigenvalue composition as opposed to decomposition. You write here the eigenvectors into a matrix E, the eigenvalue into another matrix D, and you construct these eigenvectors by knowing the normal and the tangential to the surface that you have computed, the gamma of x. Then you can modulate the deflection by modulating the eigenvalues. So I'll illustrate that with a simple example. Imagine that you have a flow which is linear going to a certain point. You place an obstacle inside. You force your function, your distance function, to be exactly 1 at the boundary. That means here it's around the circle, you have gamma equal 1. That means that outside, the free space has a function which is strictly positive and strictly bigger than 1. And inside it's inferior to 0. When you apply this modulation function as described here, here is the result that you're getting. Your flow is deflected, moves around, slides around the obstacle, but still converges to the attractor. I'll go fast. In the paper that you see, the previous one, in this one, the RAL paper, we described how we could also modulate this with moving obstacles and with multiple obstacles. And we have a new version of this for composing with very fast moving obstacles, such as pedestrian here. And what you see here is a robot traveling in a crowd. You don't see the robot is moving around. We're detecting the pedestrian using a simple detector based on vision and LiDAR, based on YOLO, which is the state-of-the-art machine learning technique for pedestrian detection. At runtime, we observe all these pedestrians and we compute a deflection of the path to avoid all of them. The last thing that I would like to mention briefly is that this dynamical system control allows you to control in Cartesian space, in velocity space, in kinematics, but it also allows you to control in force. And we've done quite some work recently on using it for force control. So before I move to force control, I'd like to mention first that we exploit extensively the notion of compliant control that we inherit from platforms such as this one that has the ability, the crooked arm here can be moved and remain compliant. So we can exploit this compliance to move the robot at runtime. The first step that we did was to use this compliance to switch across different models of dynamical systems. So you see at top that we could have 4 different models for the dynamics of this robot. It could be doing a circular polish or linear polish. And so we can, at runtime, detect this different system. Oops, doesn't seem to stop. Okay, I'll have to go back. The video is not starting. So we use the compliance to drive the system. As we show to the robot what we want it to do, it recognizes that it's a linear polish, and it runs with the linear polish, for instance. Then this frees the human, it can do something different. When the human wants to control for whatever the robot is doing, it can stop it using this notion of compliance, and then push the robot to do something else. This can be recognized as a new dynamical system. And you can switch across linear polish, retreating to a 0 position, going back down, push down, or doing circular polish and many different actions like this. So you can have a set of these actions, but these are purely in kinematic. So in order to use this action to now be able to control in force, what we did was to extend the dynamical system by explicitly controlling one part of the dynamics in the normal direction against the surface with the dynamical system. In other words, we are decomposing the flow of our motion now between a purely kinematic motion, sliding along the surface of an object, for instance, that's reaching, moving to the surface, and then a secondary component still composed of the dynamical system, which will apply the force. Now, once we have such a system, we can use the coupling across the system for 2 arms and get what you're seeing here is a pair of robots that can support an object, apply the force that you need to apply to support the weight of the object. They remain compliant, but this compliance is inherited from the dynamical system. It's the coupling between the 2 arms. It's a coupling in orientation and position, which allows them to stay oriented with respect to each other. That allows them to come back, as you see here, as soon as you break the grasp, to come back to the object. They can also adapt to a change in the orientation and position of the object for the same reason that we've discussed before in free motion. But now they have the additional capability to also apply forces and to rebalance the force once they are in contact with the object. We use this also in conjunction with a similar control system as what I described for stabilizing the center of mass, but making sure that the center of mass of a human robot remains within the polygon of stability while still holding the object within the hand. So now the 2 arms of the robots act as the 2 end effectors that need to synchronize and grab the object. You see here they do grab and hold the object. On top of that, we have to control for the bending of the robot and making sure that it bends and does not fall off the polygon of stability. But you inherit from this dynamical system the ability to adjust at runtime the position of the 2 arms to still hold the object, as you see here, if you generate disturbances on both arms. This was extended by the group of people whose names are mentioned here. So Nadia Figuerea, Salman Faraji, and Michael Koptev, for also allowing the robot to navigate and adapt its navigation. Observe, I draw it on the left-hand side, that we have a dynamical system for the navigation. It's a 2D system. This is the simplest one we could ever think of. So the robot has to navigate to this desired trajectory. It can be perturbed the same way as what we have with the dynamical system for controlling arm. You can perturb it, move it away from the desired trajectory navigation space, and we'll come back to it. And in addition to this ability to stabilize its own motion, it has the ability to also stabilize the forces that it's applying with the two arms, such that it can continue carry and move around different objects. This was a lot, a little time, so I wanted to very briefly give you this overview. We are now publishing a book that is supposed to be a textbook, so if people want to teach these different methods, they're all documented. We have a set of software along the book that shows you all the different dynamical system approach, from controlling one arm to controlling two arms to controlling in synchronization with an object, to be able to navigate in the room, and also to do force control and impedance control. I must thank really all the team behind that. There are many more people than those listed here, but these are the key people for all the work that I've presented here. All the source code is available on our webpage, tutorials as well publication videos. I'll stop here. I hope we have still time for questions. Maybe I'll stop sharing.
Thank you very much, Aude. I'm very, very sorry. Unfortunately, we do not have time for questions because of the mishap at the beginning. But really, I want to thank again Aude Billard for a truly outstanding talk. Really amazing work. Congratulations to you and to all your team. Fantastic. Thanks. And thanks again for being here. I really appreciate it. Thank you very much. Bye.